Okay, we now come to the seventh lecture. This lecture basically will now start to look at the analytical method for CAM synthesis. So far, we have been looking at effectively the graphical method for CAM construction given a follower motion. So now we are going to essentially do this primarily through writing general equations and then simply plotting them using Excel or any other kind of a software. So let's go through this. So if you recall, we had earlier derived from using polynomials for follower motion. We imposed continuity of velocity, acceleration at various transition points, apart from of course the displacement itself. And then we got the following form. We derived this, right, which is called the 3 4 5 curve, because it has a cubic, quartic and a quintic powers in the polynomial. So everything normalized with respect to theta by theta I here, which is where I is the theta I is the rise period over here, and of course here it is theta r, which is the return period for the follower. Gamma is of course defined, as I will show you, is theta minus beta, where beta is theta I plus theta d. So all of these we showed you. So we were able to get this expression for y of theta. We also had the expression for so let me see if this presentation will work. It doesn't work. So view, we'll say fit page. Yeah, so the velocity is simply the derivative. It will be dy. When I say velocity, actually I am deriving the expression for dy by d theta. Remember, dy by dt is dy by d theta into d theta by dt. The cam basically is rotating. We are right at the beginning I stated that the cam is going to rotate at a uniform angular velocity omega. Therefore dy by dt is simply a scaled version of dy by d theta, omega times dy by d theta. So the expression for dy by d theta, of course, if you do the derivation, this is what the velocity expression is going to be. Obviously in the dwell periods the velocity is going to be 0. You do one more derivative, d square y by d theta square is going to be, remember, dy by dt is omega dy by d theta. So if I do d square y by dt square, it is going to be omega square times d square y by d theta square. So the so-called acceleration is going to be essentially a scaled version of the acceleration is going to be a scaled version of the d square y by d theta square, which I am calling as y double prime. So this is the expression for y double prime. All these we derived earlier. I am just showing this again just for the sake of completeness. We did this before. The 3 4 5 curve based follower motion looked like this: smooth transitions from at the beginning, and again at the dwell. Velocity and acceleration are such that it goes to 0, it rests, and then again at this transition I have 0 velocity, 0 acceleration, then I start and then over here again reaching the dwell, we will have a situation where it is going to go to 0 velocity and 0. So these curves we had shown earlier. Again, these are plots that I had shown you earlier. We are just reproducing. I'm just reproducing this here to jog your memory rather than go back and look at those videos. I'm just reproducing that. We can see that the velocities and acceleration, which is basically in the dashed line, they all reach 0 at the various transition points to maintain the continuity of the cam profile. Now a similar expression we had derived for cycloidal profile, and again I am reproducing it here. This is the displacement equation. Similarly, the velocity, when I say velocity, I am really calculating dy by d theta. You simply multiply by omega to get the velocity. Similarly, acceleration, you take the d square y by d theta square and multiply that by omega square, you will get the acceleration. Uh, these look very similar to the 3, 4, 5 curve, the velocity accelerations out here. Now we go back to the design. So you remember we started off with this in the follower motion, and then we said, okay, look, graphically I'm going to construct the cam for a radial roller follower. Then we did a cam with a offset roller follower. So we are going to now start off an analytical method rather than rely on the graphical method. We are going to develop analytical equations first for the pitch curve. Remember that the pitch curve is the trace, is the locus of the trace point as the cam rotates. So obviously the trace point for a roller follower is going to be the center of the roller. And we do this first. We will do this for the roller follower, radial follower, and then we will do it for the offset follower. And the fundamental idea is again to use inversion. Remember, in graphical construction also, we basically stuck with the idea of an inversion. We thought of ourselves as sitting on the cam and then said what happens when the follower starts to rotate around, right? So let's say the cam is rotating anti-clockwise. It could be rotating clockwise, doesn't matter. But then the inversion appropriately will change direction. If the cam is rotating anti-clockwise, in the inversion, the follower rotates clockwise, and vice versa. If the cam is rotating clockwise, then the follower rotates anti-clockwise in the inversion. So let's imagine this frozen at some angle theta. That's what we are going to do. So it's a fairly simple visualization. Remember what we did. If you look at now, imagine that the cam has rotated anti-clockwise actually by an angle theta. Therefore, now the follower in the inversion rotates through an angle theta. In the meantime, it would also move from the pitch curve by an amount of y of theta. So originally, the at theta equal to 0, the vertical, this is the radial follower. So the follower is in the actual cam follower system is translating back and forth like this, but because we are now sitting on the cam, this starts to rotate clockwise. The follower starts to move clockwise around like this. So we are taking a snapshot after it as the cam has rotated through an angle theta, which means the follower is in the inversion rotates clockwise through an angle theta. Now initially it was the trace point was sitting at the on the circle pitch curve on the pitch curve, which is basically this circle, prime circle. It's sitting on the prime circle. Now after rotation through theta, the follower has basically now moved by a distance y of theta along the radial line, which is now this is the radial line in the new coordinate system. So we attach a coordinate system x1 y1, which is in the rotated position. Now I want in this the trace point coordinate, if you can look at, is along the y1 axis, which is basically rp plus y of theta. So essentially in the x1 y1 axis, the x coordinate is 0 for the trace point, and the y coordinate is rp plus y. Therefore you do a rotation transformation, which is the transformation matrix basically will be of the form xp yp equal to cos theta sin theta minus sin theta cos theta multiplied by I will call it as the local coordinate x1 and y1, right? So now x1 is 0, therefore the xp, which is in the fixed coordinate system, capital XY coordinate system, is simply rp plus y of theta into sin theta. So that is the pitch curve coordinate at an angle theta. Similarly, yp is going to be rp plus y of theta into cos theta. So this, of course, now the beauty of this is now we simply have a parametric equation for the x and y coordinates of the prime pitch curve. And once I know y of theta, which we have already seen, we first start with y of theta. I now have the pitch curve which I can draw analytically. And if you recall, in the previous two videos, we had gone through the graphical construction of this. I am going to show you next a picture what happens if I compare this, if I plot this equation and then compare with what I came up with graphically. That is shown in the next slide. So you can see that the stars are basically what I got from my graphical method. I have taken the GeoGebra construction that I did, looked at a few points along the curve. Actually I've taken more points than this, but I'm just showing I've left out a few points so that it is not cluttered. You can see that we have not done a shabby job with the graphical method. Of course, the analytical method is more accurate because it's based on a formula equation. So you can see that the curve, the cam pitch curve is for this roller follower, the design that we did. Remember the roller follower design, if you recall. Let me tell you again that we decided that we'll have a base circle of 35 mm. We used a roller which is 5 mm radius. So effectively the prime circle radius was 40 mm. So this is what we started off with for our design, right? In this case you can see that effectively I have quite a good match between the pitch curve what I generated earlier graphically to what I got analytically. So therefore we kind of have a good feeling that okay, two different methods are giving us the fairly almost the same curve. All right, let's now look at the offset follower for the pitch curve, and then we'll of course the pitch curve is the starting point. We still need to derive what is going to be the cam profile that has to be derived. We'll go to that, but let's look at the pitch curve with an offset follower. So now if you notice in the graphical construction, what did we do? We drew the prime circle, which was 40 millimeters radius. Then we were looking at an offset of 25 mm, which is what, so this green circle that you see is basically, if you recall in the graphical construction, we first drew this green circle of radius E, which is 25 mm in this particular example that we had worked out for the graphical case. Now remember that the translation axis is now tangential to this green circle. So if I look at this initially, the translation axis is out here in the fixed coordinate system, so it will translate up and down at this location. So this is what we will see. But now again we are going to do the same inversion issue, so which means I freeze the cam, so therefore the follower is going to rotate anti-clockwise, but at each position a theta that I have, the follower axis, translation axis, remains tangential to this offset circle. So if I call this prime circle, this green thing I'm going to call as an offset circle. So the translation axis always remains tangential to the offset circle. So what we have done is, remember in the radial case the angle was marked off from the vertical. This was true in the graphical construction also. And in the case of the offset follower, the angle is basically marked off from the horizontal case here. So this is the horizontal reference that I have. And then let's say I moved by an angle. So obviously I'm marking an angle theta clockwise because the cam is assumed to rotate anti-clockwise. And if I draw the follower is basically now along this axis, and it has moved by an amount. So the lowest position occupied by the follower is at a height d from this point C. So that is given by, if you look at Pythagoras theorem, the radius is basically rp, which is the prime circle radius, and e is the offset. So therefore d equal to root of rp square minus e square. Of course this is a more general form. If you substitute e equal to 0, then d becomes rp, which is what is the radial follower case. So one could straight away derive an offset follower expression and then treat the radial follower as a special case where e is equal to 0. So that can be done, but we kind of went through the easier one so that you get a feel of this, and then of course we derive this. But if you have these equations, you can treat the radial follower as basically a special case of e equal to 0. Now, so if you now look at the coordinates along the x and y axis, remember that everything is being marked. The xy axis is out here, and the x1 y1 axis is basically out here. So if I look at along the x-axis, this point is the coordinate of this point f. It is moved from the center A by the amount e, and then along the y-axis it is now got a coordinate of d plus y of theta, which is what is shown in the next slide. So we have the pitch curve for the offset follower. The roller center has translated to position f, which is out here. the coordinates of the roller, the trace point is basically E along the x-axis. So remember, A to C is basically E. Then CF is basically D plus Y of theta. So this is the local coordinate. So now we apply the same transformation matrix. Remember, XP, YP is going to be cos theta, sin theta, that's the first row, minus sin theta, cos theta, second row, multiplying x1, y1. x1 happens to be E and y1 happens to be D plus Y of theta. Therefore, when we transform to the fixed axis, the pitch curve coordinates become E cos theta plus D plus Y of theta sin theta, and similarly YP will be minus E sin theta plus D plus Y of theta multiplying cos theta. So as I said, if you now put E equal to 0, D becomes RP, and you get back the same equations that were there for the radial follower. So so the more general form, which is the pitch curve with offset, you can get the radial as a special case by putting E equal to 0. Again, let's look at what I got graphically, I constructed, and let's look at what we get analytically. So that is shown in the next curve. Not too bad. Some of these you can see my curve fit in the graphical was not so great. So there's some small deviations, but overall you can see that the general shape is captured by the graphical method. The graphical is always going to have some errors. It is never going to be very exact. So that's something that you have to keep in mind. All right. So so you can see that we have in fact very simple equations for the pitch curve of the cam. What we will do is to move into uh, the next lecture. What we'll do is, having got the pitch curve, of course the interest is not going to stop only with the pitch curve, but we now have equations for the pitch curve. So with this equation, now of course I want to get the cam profile, because that is the equations for the cam profile is the most important thing that I'm bothered about. What did we do in the graphical construction? Remember, we had points on that the pitch curve. At each of those we drew circles, and then we drew a tangent basically to get the cam profile. So we are going to now go with that step. So if you ever wonder why should I do a graphical thing, it kind of gives you the idea of what goes behind deriving the analytical method. So let us stop here. So and then let us in the next thing we will take off from this pitch curve equations and then see how to derive the cam equations.